Hi and welcome back again. Previously you learned what a quadratic form is, how it is related to a symmetric matrix, and how to find the principal axes of the quadratic form. In this video we will use these principal axes to distinguish between different types of quadratic forms. Consider the following 5 graphs of quadratic forms. You immediately notice that they show very different behavior. The 2 graphs on the left only take non-negative values, while the 2 on the right only take non-positive values. Meanwhile, the one in the middle takes both positive and negative values. Moreover, the ones in the bottom left and bottom right are only 0 at the origin, while the ones on the top left and top right are 0 for more input factors. These 5 types of behavior are precisely captured in the following definition. Consider a quadratic form Q. Then we call Q positive semi-definite if q of x is bigger than or equal to 0 for all x, positive definite if q of x is bigger than 0 whenever x is non-zero, indefinite if q assumes both positive and negative values, negative semi-definite if q of x is less than or equal to 0 for all x, and negative definite if q of x is less than 0 whenever x is non-zero. We use the same terminology for the corresponding symmetric matrices. So, symmetric matrix is indefinite if its corresponding quadratic form takes on both positive and negative values. Using this terminology, we can classify the 5 graphs from before. This classification comes back in various fields. Later, we will encounter it when we consider optimization of quadratic forms. In addition, if you're familiar with multivariable calculus, you might remember that you can classify whether a critical point of a multivariable function is a local maximum, a local minimum, or a saddle point by using the so-called second derivatives test. Using the terminology of this video, the second derivatives test asks you to check whether the matrix of second derivatives at a critical point, called the Hessian matrix, is negative definite, positive definite, or indefinite. From the formula of a quadratic form, it might be quite hard to check how we should classify it, especially if it has cross terms. Luckily, the following theorem tells us that we can classify a quadratic form based on the signs of the eigenvalues of the corresponding symmetric matrix. The quadratic form is positive semi-definite whenever all eigenvalues are greater than or equal to 0. Positive definite whenever they are all greater than 0, indefinite whenever there are both eigenvalues which are greater than 0 and which are less than 0, negative semi-definite whenever all eigenvalues are less than or equal to 0, and negative definite whenever they are all less than 0. We postpone the proof to the end of this video. Instead, let's consider an example. From the formula of this quadratic form, you might be tempted to think that it is positive definite, as it has only positive coefficients. However, the eigenvalues of the corresponding symmetric matrix are 3 and minus 1, so this quadratic form is in fact indefinite. Indeed, we can easily find vectors for which q takes positive or negative values, and we can also see this behavior in the graph of the quadratic form. In order to prove the classification theorem, we orthogonally diagonalize A by writing A is P d P transpose. Here P is orthogonal and D is diagonal with the eigenvalues λ1 up to λn of A on the diagonal. The principal axis theorem tells us that if we make the change of coordinates y is px, then q of x is given by λ1 y1 squared up to λn yn squared. Recall that the classification of quadratic forms was based on which values q of x can attain. Since p is invertible, the vector x is non-zero whenever the transformation y is non-zero, since each x corresponds uniquely to one y. This means that the set of all possible values of q of x for x not equal to 0 is the same as the set of all possible values of λ1 y1 squared up to λn yn squared for y not equal to 0. Whether the second expression can take on positive or negative values is clearly determined by the signs of the eigenvalues. Indeed, if for example all eigenvalues are less than 0, then the expression lambda 1 y1 squared up to lambda n y1 squared is also less than 0 when y is not equal to 0, since squares are positive. So in that case the quadratic form is negative definite. On the other hand, if the first eigenvalue is greater than 0 while the final eigenvalue is less than 0, then choosing the vector y, which has a 1 on the first component and 0 otherwise, leads to a positive value, while choosing the vector y, which has a 1 as its last component and 0 otherwise, leads to a negative value. So in that case the quadratic form is indefinite. That's all for now. Don't forget to practice the material and see you next time.